Alright, so let's go ahead and try to find some eigenvalues and eigenvectors. So first, let's go ahead and try to find the eigenvalue. So that'll be the determinant of our matrix A, 1, 1, 2, 2, minus lambda times the identity, so lambda, 0, 0, lambda, which we'd like to set equal to 0. So first, let's take the determinant of 1 minus lambda, 1, 2, 2 minus lambda. And we find this determinant, we should get 1 minus lambda times 2 minus lambda minus 1 times 2, which will be 2. And so, bringing this over to the other side of the page, we should, when we FOIL, get 2 minus lambda minus 2 lambda plus lambda squared minus 2. So negative 2 and 2 should cancel out, and we should get lambda squared minus 3 lambda equals 0. We can factor out a lambda to get lambda times lambda minus 3 equals 0. So lambda equals 0 and lambda equals 3. Alright, so now we want to go ahead and find those associated eigenspaces for those eigenvalues. So for 0, we would like to go ahead and find the null space for the matrix minus 0 times the identity, which in this case is just the null space for the matrix. And so if we try to find the null space of this matrix, we'll take 1, 2, 1, 1, 2, 2, augment with zeros, get the reduced row echelon form of 1, 1, 0, 0, 0, 0, and that tells us then that x equals negative y. So x plus y equals 0, and that tells us then that x equals negative y. So then we have the set of all x, y such that x equals negative y, which is the set of all negative y, y such that y is an element of the real numbers, which will just be the span of negative 1, 1 for our eigenspace associated with 0. There's one of our two eigenspaces, and we'll want to go ahead and be able to find the other one as well. So if we want to find that space, the eigenspace associated with 3, we're trying to find the null space of A minus 3 times the identity. So this is the null space of 1, 1, 2, 2 minus 3, 0, 0, 3, which will be the null space of negative 2, 1, 2, negative 1. And so if we went ahead and tried to take and find this null space of negative 2, 1, 2, negative 1 with zeros augmented, the reduced row echelon form, or at least something close to the reduced row echelon form, will just be 2, negative 1 in the first row with zeros otherwise. So y is a free variable again, so we have 2x minus y equals 0. So x equals y over 2 when we solve for it. So then that tells us that we get our null space is equal to the set of all x, y such that x equals y over 2, which will just be the set of all y over 2 y such that y is an element of the real numbers, which is just the span of 1/2, 1. So that'll be our eigenspace associated with the eigenvalue of 3. Alright, so there's one of our examples down. So let's go through the other one as well. So say we wanted to go ahead and find the eigenvalues for this matrix A of -2, 4, 3, -1. Again, we're going to start our process the same way we always do, finding the eigenvalues first. So we're taking the determinant of -2, 4, 3, -1 minus lambda 0, 0, lambda, so just lambda times identity. So this will be the determinant of -2 minus lambda, 4, 3, -1 minus lambda. And so that determinant will be equal to -2 minus lambda times -1 minus lambda minus 4 times 3, which will be 12. So remember, finding these determinants, we take, since it's a 2 by 2, top left times the bottom right, minus top right times the bottom left. And so foiling this together, we get 2 plus 2 lambda plus lambda plus lambda squared. So a lot of negative signs to be careful of. Negative times negative gives positive, negative times negative gives positive, negative times negative gives positive, and negative times negative gives positive. And then minus 12. So we should end up with lambda squared plus 2 lambda minus 10 equals 0. So when we're trying to factor these, something to keep in mind and remember is that our numbers need to multiply to -10 and add to positive 2. So if this is negative, that means the signs don't match. So one of these is negative and one of these is positive. And if it's a positive number, the larger number should be the thing that is equal to is the positive number. Now, running into an issue, I'm wondering if I did this correctly. Because 5 times 2 is 10, but that should give us... This is good. We're going to work through the process and see what sort of issues may or may not have arisen. So we've got that minus that minus that's good. 4 and 3. 4 times 3 is still 12, last I checked. -1 times -2 will be a positive 2. When I added these, I forgot to add them. So it should be 3 lambda. That makes a lot more sense. So remember, it's okay to make mistakes. You just want to be able to backtrack through your work and figure out what the heck happened. So if it's 3, we should have 5 and -2. So we've got -2, or 2 minus 5, blah, 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 blah. Lambda minus 2 times lambda plus 5 equals 0. So that means our eigenvalues are lambda equals -5 and lambda equals positive 2. Okay, so we want to find our eigenspaces associated with each of those eigenvalues. So for the eigenspace associated with -5, we want to find the null space of A minus 5 times the identity. So that'll be the null space of -2 minus 5, 4, 3, -1 minus 5. Oh, -5, we should be adding those because we're usually subtracting. So A minus lambda I, since it's a negative lambda, it'll be A plus 5I. So we add those, we get the null space of the matrix 3, 4, 3, 4. Wonder what that's going to end up being when we try to find it. So we've got this matrix 3, 4, 3, 4, 0, 0. Get it into a reduced form. We'll get 3, 4, 0, 3, 0, 0, 0. Man, I am all about making tiny little mistakes in talking today. Alright, so that means that 3x plus 4y equals 0, so x equals -4/3 y. So then that tells us that the null space is the set of all xy such that x equals negative 4/3 y. So we have set of all negative 4/3 y such that y is a real number, which then tells us that for the span negative 4/3 1, this will be equal to the eigenspace associated with negative 5. Alright. Be careful with those negatives, they'll get you sometimes. They'll even get me. So if we want to find our other eigenspace, the eigenspace associated with 2, we want the null space of A minus 2 times the identity. So that's the null space of negative 2 minus 2, 4, 3, negative 1 minus 2. And so that is the null space of the matrix negative 4, 4, 3, negative 3. So when we go to take this matrix and simplify things down, we should get 1, negative 1, 0, 0, 0, 0, which gives us the equation x minus y equals 0, so x equals y. So then that means we have the set of all xy such that x equals y. And so with that constraint then we have set of all y such that y is an element of the real numbers. At this point you're asking, why the heck do we have to do all this? That is a great question. It's because we want to get to a point where we can diagonalize a matrix. That'll be for next week. So this is the span of 1, 1. So that'll be our eigenspace associated with the eigenvalue of 2. So those are going to be our processes for trying to find some eigenvalues and eigenspaces. If you want, for extra practice, you guys can kind of throw other matrices in the discussion board and see if you can find the eigenvalues and eigenvectors for those.